the previous work we looked at CRD for complete randomized design. And we indicated that this design is suitable to controlled environments such as laboratory and greenhouses. Because it doesn't involve blocking, no blocking for this. And remember, blocking is the only principle that excludes the effect of an intruder or the external. Now, suppose that we are to lay down an experiment in an uncontrolled environment. Uncontrolled environment. What do we mean by uncontrolled environments? We are referring to the field, for example, the open field in agriculture. The open field in agriculture, or we suspect that there could be a factor which we are not investigating, but which can also influence the results. In such a case, we need to use randomized, complete block design. In short, RCBD. Now, perhaps I need to elaborate further here. Let me give a simple example where we have an agriculture field. That's an agriculture field. Now, you will realize that when you move, let me call this point A and point B. In terms of soil fertility, let me just say soil fertility. Soil fertility. We don't expect uniformity in terms of soil fertility across a big piece of land, agricultural land. Now, if we are to say, for instance, we want to test the performance of crop varieties or simply genotypes. Let me say we've got variety 1, variety 2, and variety 3. So our treatments are the different varieties. The factor is variety. Our treatments are the different varieties V1, V2, V3. So what we are interested in is to see which variety gives us the highest yield. If we talk in the context of pearl millet or mahangu in the local language, if we've got okashana and kantana, then our interest is to see which variety, if grown, will give us the highest yield. That is what we are interested in. But let me assume that there is a fertility gradient in the land where we want to grow the varieties, so much that there is a high fertility in A and the low fertility is one move towards B. So in this case, it means if we use CRD, remember CRD, we may have a variety 1, variety 1, variety 1. If we are using 3 reps, we may have a variety 1 occupying this piece, this portion of land. that I've demarcated. And if we are using 3 replications, so variety 1 has been grown 3 times, so that is fine in 3 plots. So let me assume that variety 2 occupies this, variety 2, variety 2, variety 2, occupies that region. Already you can see that when we are comparing the results will not give us a true reflection of the performance of varieties. We will not be able to correctly compare the performance of variety 1 and variety 2. Why? Because variety 1 is grown under high fertile land. As you can see, it is where fertility is very high. So the performance of variety 1 relative to variety 2 is not only a result of the fact that variety 1 is good, but it is also due to where variety 1 is grown. So there is a design problem there. The design is not perfect. So in such a case, we need to block. What are we blocking? We need to block the effect of fertility. Instead of arranging this experiment this way, what would be the best scenario is to have a situation where we subdivide this big piece of land into what we call blocks. So this is block 1, block 2, and finally block 3. Now, what is a block? A block is the smaller part of the big experimental area, which is assumed to be uniform. So in this case, what is block 1? Block 1 is the smaller portion of the big piece of land, which is uniform with regards to, soil fertility. Now, what then do? We need to make sure that each treatment appears in a block. Remember, we are talking of complete block. Complete block. The block must be complete. So because we've got variety 1 and variety 2 and variety 3, we need to ensure that both varieties should appear in each block. So because we are randomizing, remember this is complete randomized block design. So we are randomizing within a block, and we make sure that each treatment appears in a block. So we will have variety 2, variety 1, variety 3 appearing. So in other words, you can compare the performance of variety 1, variety 2, variety 3, because all of them are subjected to high fertility. Now, in block 2, because we are randomizing, we can have V1 coming first, V3 second, and V2 coming third. In block 3, we will have, for example, V3, V2, and V1. This is the randomization results in this haphazard distribution of the treatments in the block. But the principle is that the block must be complete. Complete means each treatment must appear in that particular block. That is the meaning of complete. But we must be randomizing. So in this case, it means we have excluded or gotten rid of or blocked the effect of the variation in fertility. So in this case, we have excluded fertility gradient. We've excluded fertility gradient because each variety is being subjected to almost similar conditions. Ladies and gentlemen, this is what then we call randomized complete block design. There are so many things that can be blocked. Here, I've just given an example of fertility gradient. If we go to animals, and we've got 12 animals, which we want to use in a feeding trial, what it simply means is that if the animals are not of the same age, then it means we need to make sure that we block the effect of the age. If we have got feed 1, feed 2, feed 3, that we want to compare, it means we need to create a block where we put age group 1, age group 2, age group 3 to that. We do the same here. Age group 1, age group 2, age group 3. We do the same here. Age group 1, age group 2, age group 3. At the end of the day, you can't say weight gain has been influenced by age. So we can't conclude the performance of feed 1, feed 2, feed 3. No, because feed 1 has been given to all the age groups. Feed 2 has been given to all the age groups, and feed 3 has been given to all the age groups. That is what we call randomized complete block design. So in the next segment, we are going to look at this subdivision. How do we split the sum of squares? How do we split the sum of squares? Thank you very much. I'll stop recording for now so that we. So, and I want you to take note that blocking, what needs to be blocked can be anything. What needs to be blocked can be anything. Anything that has got the potential of influencing our results, but it's not being investigated. So what we have on the screen there is an example where we need to use to fit an ANOVA for RCBD. I'm sure the words are a bit small, but I'll try to read. In an experiment to compare, this is the example. In an experiment to compare the effects of 4 drugs. So we've got 4 drugs, the effects of 4 drugs, A, B, C, and a placebo, or inactive substance D, which is being used as a control. You see, that is a placebo. And D, on lymphocytes counts. A randomized complete block design with 4 mice from each of the 5 litters were used. So we have the mice that are coming from different litters. The litters being the blocks. So in other words, the mere fact that the mice is coming from a different litter is a source of variability. Is a source of variability when with regards to the lymphocyte counts. So if a mice is coming from litter A and from litter and another one from litter B, automatically we expect the lymphocyte counts to be different because of the litters where they are coming from. But what is our interest? In the experiment, we want to compare the effects of 4 drugs, not the litters where the mice are being taken. So the data is shown here. We've got liter 1, 2, liter 3, liter 4, liter 5. Drug A, B, C, D. So the question is to set up the two-way ANOVA. Set up the two-way ANOVA. So the two-way ANOVA, it means we want to see if blocking by liter is effective, and also if drugs are significantly different from each other. Now, let me give you the general ANOVA for an RCBD. But this is the example that I will present in a separate video. But for now, I'll just give you the general ANOVA table for an RCBD. Then I will give a specific recording tackling this particular example and showing you how to calculate the different sums of squares for a two-way ANOVA. Now, let me say RCBD ANOVA. To be more specific, let me say two-way ANOVA. And I will explain why we call it a two-way ANOVA. Now, let me assume that we've got, like the example that I've given you, we've got our treatment. Treatment 1, 2, and so on, maybe up to T. There are T treatments. And we've got blocks, call them blocks. We've got 1, 2, and so on up to B, right? So with that one, we have our Y11 as usual, Y12 up to Y1B. We have Y21, Y22 up to Y2B. Then we've got YT1, YT2, and so on up to YTB. So to get our ANOVA, we will need the totals, right? We need the total, the treatment totals, and we need the block totals. Let me call totals here, the block totals. So this will be our Y.1, Y.2, Y.B, right? These are the totals. Then we will have our Y1 dot, Y2 dot, and so on up to YT dot. The total of the totals, we call it Y dot dot, which is our grand total. Like before, the correction factor is given by Y dot dot squared over T times B. Remember, T times B is equal to N, number of observations. So if we multiply the number of treatment by the number of blocks, we are going to get the total number of observations for this particular experiment. So the correction factor is Y dot dot squared over TB. Now, the SS total will be given by summation of Yij squared minus the correction factor minus our correction factor, right? Then here we are going to get the SS, the sum of squares due to treatments. So SS treatments. This will be equal to, now we are going to get the treatment totals. So call it summation of Yi dot squared divided by the number of blocks B minus the correction factor CF. So we are adding this plus this squared plus this squared. These are the total. This squared plus this squared plus this squared. We divide by the number of blocks. So that's why we are dividing by B. You count the number of blocks. Okay. Then SS blocks. will be equal to the summation of y dot j now squared over the number of treatments minus the correction factor. So we are squaring. For blocks, we square this plus this squared plus this squared plus this squared. We divide by the number of treatments. That is very, very important. And we subtract the correction factor. So in short, the total sum of squares SST will be broken down into SS blocks plus SS treatment plus SS error. So there is unexplained variability. This is total variability. So total variability is due to blocks, differences in the blocks, and also due to treatment, and finally due to error. This should be very clear. So we have only added the component. We have added the component of blocks. So you would realize that the degrees of freedom for total will be BT minus 1. BT is the number of observations minus 1. The degrees of freedom for blocks, now I'm talking of the degrees of freedom because these are needed for the ANOVA. For blocks will be B minus 1. For treatment would be T minus 1. For error, it will be B minus 1 multiplied by T minus 1. This is very, very important. So our ANOVA table will have source of variation. So the source of variation will be 1 from treatment, from blocks, error, and then total. This is clear because we can see the total, blocks, treatment, error. Now, the degrees of freedom, T minus 1, B minus 1, T minus 1 multiplied by B minus 1, BT minus 1. Now, our sum of squares, the SS treatment, SS block, SS error, SST. Mean sum of squares, it will be SS treat divided by T minus 1. This is very, very important. Each sum of square is divided by its degrees of freedom. SSB divided by B minus 1. SS error divided by T minus 1, B minus 1. Now, we will have our F. Now, take note that because the two-way ANOVA, we will have two F values. There is the one for testing the significant differences in treatments, which is SS treat over T minus 1 divided by SSE, but SSE will be divided by T minus 1, B minus 1. So we come again to blocks. We will have our SSB over B minus 1. This will be divided by SSE divided by T minus 1, B minus 1. So take note that this is a two-way ANOVA because we now have two F values. There is this one and there is that one. And all these can be obtained using this formula after laying down your data in that way. So I think it is important that I'll make a follow-up video where I will demonstrate a numerical example of how to get the different sums of squares for a randomized complete block design, or simply a two-way ANOVA. Two-way ANOVA because we now have two F calculated values. One for testing the hypothesis of equality in the means across blocks versus non-equality of at least one mean from the rest. And also the other F for testing equality of means across treatments versus at least one treatment mean being is not equal to the rest of the other. Thank you very much and enjoy.